Sixth grade, welcome to science class. We're cruising along through chapter 15 here. We've been talking about all the different forces and types of motion that we have. We've talked about gravitational forces with tides. We've talked about motion and friction that's against motion. We spent some time talking about speed and learning those science terms. Today we're going to talk about the laws of motion, and we're going to study Newton's three great laws of motion. And today we're going to take the first one. So we're after this major aim question, what are the laws of motion? We get this review statement, or I should say summary statement. A force is needed to change an object's motion. An object accelerates in response to a force on an object causes an equal but opposite reaction force. So that's one of Newton's laws that we're going to talk about, guys. And then just a reminder, if there's going to be some kind of change, you need an unbalanced force. Remember, accelerate is a change in speed or direction. And we'll learn about that as we go our way through that. Hopefully you got your notes out. Here we go. For hundreds of years, scientists tried different experiments to try to explain motion. One of those scientists was Galileo Galilei, who in the 1600s studied falling objects and the idea of gravity. So you have number one in your notes, guys. Okay, he studied gravity and how it works. Here's what Galileo did. If I can go back to lesson 1 here, guys. Right here is where Galileo worked. He climbed up the Leaning Tower of Pisa where he could drop things straight down, and because it leaned, you could drop things straight down and it would fall away from a building. So he didn't throw things out because that would change motion. He just dropped it straight down. So you got extra credit already. Write down Galileo and the Leaning Tower of Pisa. It's up here. If you're wondering how in the world do I spell the Leaning Tower of Pisa, that's the city, and now today it's a famous Leaning Tower. They didn't build it that way, guys, but shifting grounds and gravity works wonders. Second interesting thing about Galileo, he's remembered for his first name, not his last name. Most famous people are known for their last name. Like we are going to study Newton's laws of motion. We're not going to study Isaac's laws of motion. He's a normal person. He's known for his last name. Galileo, for whatever reason, known for his first name. Cruising on. At the time, people thought that objects slowed down and stopped by themselves. They couldn't explain why they stopped. Why? They didn't understand friction. Number 2 in your notes. It wasn't until 1686, so a little bit after Galileo, that Isaac Newton published his book. His book was called Principia, what we would call principles today. In it, he related forces to motion of objects. Newton's book put the ideas of many scientists together in a way that people could understand them. Number 4 in your notes. Guys, that's the biggest thing. There are a lot of scientists out there that write books or magazine articles for each other. In other words, the average person can't read them and understand them, so it flies over their head. Newton said the average person can read this and understand it because I'm going to write it in such a way that it gets down to the basics. Newton's first law of motion describes the motion of an object that has equal forces acting on it. Here is Newton's first law of motion. An object at rest remains, number 5 in your notes, remains at rest. And an object in motion will remain in motion at a constant speed and in a straight line unless acted on by an unbalanced force. So you got 3 blanks you were filling in for number 5 there, guys. We like to say an object at rest stays at rest, an object in motion stays in motion unless a force acts on it. And that force needs to be unbalanced because it needs to do something to it. All right, let's try to explain that now. It says, the first part of this law is not surprising. You know that if you place your book on your desk, your book is at rest. The book will not move unless you pick it up or another force acts on it. In other words, it will remain at rest. If I don't do anything to my book, it sits on my desk. If I lift the book, then it moves. If I lift my desk, the book falls off it, right? We like the slide game and it tumbles to the floor. Something acted on it. Okay, so we see that all the time. If you place a soccer ball on a field, you have to kick the soccer ball to get it to move. So number 6 in your note, that's not surprising, guys. That's common sense. Things sit still. They don't just start to move by itself if it has any kind of weight to it. We'll then move on and say, okay, so let's continue this. The second part of the law may surprise you. An object stays in motion. An object in motion stays in motion. Motion in your everyday life doesn't seem to obey Newton's first law. Number 7 in your notes. Let's give an example. If you kick a soccer ball, it moves for a while, but it slows down and stops. It doesn't stay in motion. Maybe you want to think about riding your bicycle. To keep your bicycle moving, you have to keep pushing on the pedals. Now I get it. Oh, not if I'm going downhill, Mr. Bauer, it just goes by itself. Okay, great. That's talking about the forces acting on it. And so what we're saying is, guys, if I want to remain in motion, I have to keep things happening to it. So did Newton get it wrong? Why do the objects slow down? Well, one is friction. Objects in motion can be stopped by friction. Now, friction is anytime two things are touching. When your bicycle wheels touch the ground exerts a frictional force. Air friction also slows the motion as air particle pushes against the bicycle. And other forces, such as gravity, may also slow an object's movement. So you got stopped by friction here, and then you did air friction and gravity may also slow an object's. In other words, Newton says, hey, an object in motion will remain in motion unless forces are acting on it. But guys, forces are always acting on it. Okay, gravity is always pulling. The air always has pressure. There's always air particles I'm moving through. All those things are slowing me down. Now, those same forces, guys, are working on the book that's sitting on your desk as well. But the air pressure isn't strong enough to just push the book off your desk. Gravity can't pull that book through your desk so it goes to the floor. And so you got to understand, there's always forces going on those things. Okay, now you have your vocabulary word for it. Newton's first law of motion is sometimes called the law of inertia. Make sure you say that word properly and know that word. It's spelled a little goofy, but sound it out, inertia. What is inertia? Inertia is the tendency of an object to remain at rest or in constant motion unless a force acts on it. That's number 9 in your notes. I like to say, what is inertia? Keep doing what you're doing. So if I'm in motion, I stay in motion. If I'm at rest, I stay at rest. Inertia says just keep doing that. Because ice has little friction, inertia allows an ice skater to glide long distances. The skater is in motion. There's not too many forces acting against it because there's not a lot of friction with the ice. And away we go, gliding. A rock sitting on the ground stays still. Why? Because it's the tendency to keep doing what you're doing. The rock is at rest. It wants to stay at rest. Suppose you had 2 jars of the same size. One is filled with feathers, the other is filled with pennies. Which jar would be harder to move? If you said the pennies, you're right. Why? Both are the same size. The jar of pennies, though, is more difficult to move because it has more mass. The amount of inertia an object has depends on its mass. Number 10 in your notes. The more mass, the greater the mass of an object, the greater its inertia. In other words, the greater it's going to keep doing what it's doing. Okay? Inertia, guys, lots of times goes along with what we're going to talk about on Monday, which is momentum, to keep doing what doing. But you think about a rail train. Okay, if there's something on the tracks, guys, they can hit the brakes, can't they? But your train is not stopping for a long time. Why? It's going to keep doing what it's doing because the greater the mass, think how much a train weighs. It takes a long time to stop doing what it's doing. So it was in motion. It takes a long time to stop that. It's the same thing if you then reduce the weight down. A car can stop faster than a semi. Why? Semi has more mass. Okay, now we're going to put this in and we're going to help you understand number 12, how we do examples of inertia. It says, this crash test dummy shows the effects of inertia. If a car stops suddenly, the forward motion of the people in the car continues. The force that stopped the car does not stop the people inside the car. The force of the seatbelt, or in this case also an airbag, that'll stop a person's motion. Now let's understand that with inertia, guys. I'm in a car and I'm cruising at 50 miles an hour. My car slams the brakes. What just happened to the car? The car stopped. What does inertia say? I want to keep doing what I'm doing. Well, what was I doing? I was moving forward at 50 miles an hour. And so here's the challenge. In a car, the driver suddenly slams the brakes. Number one, wrong brakes there, isn't it? Circle it. B-R-A-K-E-S. This is like I broke something in half, or I took a snack break. This is not the brakes of a car. Sorry about that. Anyways, back to refocusing. The driver slams the brakes. You're sitting. What does your head do? Does your head stay where it is? Does your head go forward? Does your head go back? Does your head swing to the left? Does your head swing to the right? So picture yourself driving in the car. They hit the brakes. What is your head going to do? B. Now you're sitting at a stoplight. And picture yourself in a race car. Might be a better idea. It turns green. The driver says, I'm going to try to get to 100 miles an hour, and slams his foot on the pedal to try to win the race. You're sitting there, and they slam the gas pedal. Which way does your head go? Forward, back, left, right, or doesn't move at all? Okay? It might help you to think about you're not ready for this either, so as soon as they hit the gas, which way is your head going? Now, in my mind, the hardest one. You're sitting in a car. The car turns left really fast. So he takes a sharp, fast left turn. Which way does your head go? Forward, backwards, left, or right? Okay, so you're kind of thinking of yourself as this crash test dummy here. This one might help you to do letter A. That's what just happened. The car stopped, and you can see what's happened to that poor crash test dummy's head, right? And then understand it's because your body wants to keep doing what it's doing. My car was in motion. I want to stay in motion. And so the seatbelt holds me to the seat, but there's nothing holding my head. That's why my head's going to move in this example. All right, best of luck to you learning inertia.